Okay, sharp. By now, I think we understand something, Yana, when coming to compound events. But also, I believe at this point, if you look at this formula doesn't shock you anymore. And as much as we haven't applied the formula yet, you must know that this is similar to this. The probability of A or B is the same as the probability of A union B. So the or stands for union. That's where it could be anywhere. Remember our circles from the previous video? And also the probability of A and B is the same as the probability of A intersection B. This we understand. So we have the probability of A or B, which is the same as the probability of A union B. And then we also spoke about the probability of A and B using the circles of the events on our previous video. That's when they interacted, where the events were happening at the same time or were occurring at the same time. There was this case about mutually exclusive event. If events are mutually exclusive, that's when we said they cannot happen at the same time. Meaning for a case where events are mutually exclusive, it means the probability of A and B is equals to 0, which by ways of donation, it could be the same as the probability of A intersection B is 0. This is like this. This is like this if they're said to be mutually exclusive. Because mutually exclusive means they cannot happen at the same time. So what does it mean? If you want to calculate the probability of A union B, and given that the events are mutually exclusive, you're not going to have this part, all of it, because it's 0. So this is basically what it means. If events are mutually exclusive, your entire formula will wipe that part where they're interacting, and then it becomes like this. Don't worry if it doesn't make sense. We'll get to a part where we actually do the practical examples. But then before we get there also, I want to add another story. Now, we know about mutually exclusive, which means events cannot happen at the same time. But we still have a story where two events are independent. So events can either be dependent or independent. The part where you are flipping a coin or shuffling cards, we must know is the events that you are trying to attempt at whatever point, are they dependent or independent? The story will tell. But then again, if you are answering a question paper, regardless of what I'm about to say now, if you are answering a question paper and then you get to a point where they never specify that events are independent, we always assume they're dependent. If they're independent, they will state, because for events to be dependent or independent, it's also a special event when coming to the equation. So now this is what independent means. So if now you're answering a question paper and it happens to be a statistics question paper, or it's a question that is related to statistics, and the topic that you are focusing on now, it's probability of compound events. And somehow on that question, they state that the events are the events this time around, they are independent, because mutually exclusive means P, probability of A and B is 0. So independent means that you can get the probability of A and B just by multiplying probability of A and probability of B. This means the same way. Remember, intersection means and. So to get the probability of A and B where they interact, if they are both independent, you can just multiply both the probabilities independently. This is part 2 of the video, and everything still seems confusing. I understand, it's fine. We're still getting there. We're going to break it down. But then for now, so number 1, when answering questions that are related to probability of compound events, these are the things that you should be expected to be like familiar with. You should know the intersection of two independent events, how to deal with that situation. You should know the intersection of two dependent events. You should know the union of two dependent events that are mutually exclusive. You should know the union of two independent events that are mutually exclusive and that are mutually inclusive as well. So like, I'm going to break them down one for now. Like, now that independence is still fresh in our mind, I want to make the first example that relates to independent. So I want us to do an example whereby I will demonstrate how to calculate the probability, or rather how the question comes about, of the probability of intersection of independent events. So intersection where two events combine, where they meet, same like as this formula. And I said now that the intersection of two events, when they interact, we represent it as AND. So probability of A and B, it's going to be just multiplication of both the events. So that's the first example I want us to look at, which is, so I want us to focus on this example, which is how to find the probability of the intersection of two independent events. So I want us to look at the example of how the calculations of finding the probability of the intersections of two independent events may come about. People play around to a case where they're like, if you can flip a coin twice and it lands on heads, I'm going to do this and this and this and that. Regardless of the reward, what happens if you flip a coin and you expect the coin to land on heads? Basically, if someone does that and the coins actually flips on heads, to be like, they're lucky. But now probability is calculating what are the chances of them being lucky for both the coins to get to land on heads at the same time, for the person to get the rewards of whatever the reward may be. So the first coin may either land on heads or tails. And then the second coin, it could result in a head as well, or head and tail. So the first coin could be a head, the second tail could be a head and head, or head and tails. But then also, it could also be a head and tails, or tails and tails. So these are the chances. So we say now, the sample space of the chances to get head and, you can either get head and head, heads and tails, tails and heads, or tails and tails. So out of the 4 chances, if your friend now has to flip the coins once to hope to get heads and heads, out of 4 chances, which is 1, 2, 3, 4, there's only 1 chance for them to get this. So it's going to be 1 success or 1 outcome out of 4 chances, which is basically the calculation of probability. So this is going to be 0.25, which is now 25%, right? Now, the sample space is head and head and tails, right? So we're looking at the fact that the probability of getting heads and heads is going to be probability of heads multiplied by probability of heads. And we know that for a sample space of 1 coin, it's only heads and tails, which results in 1/2 chances, either heads 1 out of the 2 chances. So we know that's going to be 1/2 multiplied by 1/2. Therefore, this means that the probability of getting heads and heads is going to be 1/4, right? Probability of getting heads and heads is equals to the probability of heads multiplied by the cause of it, which is 1/2 times 1/2, according to a single coin, which gives us 1/4, which is 0.25, which is still 25% chance. So this is what independency means. It means you can apply this formula, you'd get the same answer as this reasonable way of calculating the whole thing. I hope it makes sense now. So whenever they say events are independent, this is what they mean. Just by multiplying the events independently, you can get the probability of intersection of the events, or for the events to happen at the same time, or for event A and B, but remembering the circles of compound events. This was the first example. Like I say, I'm trying to make the videos as shorter as I can. Join me on the next video as we go to the next example. I'm Mr. Maimane. This is Simplified RSA, the guys who makes it looks easy. Please subscribe on our YouTube channel. Please like our videos on Facebook, Twitter, or wherever you're consuming this from, whichever social media platform that you're watching this from. Yeah, other than that, next video.